This is a very simple client for the microservice I wrote in Idris on top of Node.js. And currently, this has the ability of create some JSON data. And this JSON data represents an order which came from the example from the Scott Walshin's domain modeling made functional book, and I turned that book into a real Idris code using some dependent types. And if I try to submit the order first, it will fail because there is no server running. And to have a server running here, what I have to do first, I show you that I just clean this repository and I'm compiling this microservice from zero. And Idris is very fast, so that is one of my first things, that Idris can be used as a normal software development tool because its compilation times are super fast. So you see this solution consists of 35 modules, and I use Google Closure Compiler to optimize the generated JavaScript, and I started a Node.js from the generated JavaScript, and the service has started. And now if I click the submit again, now with this service responds, but actually with an error and saying that, oh, there was some placeholder error, and going down, SQLite tells me that the customer email constraint has failed. And what happens here on the service side, that we are getting this JSON from the client, we do some transactions and some ID generation, we generate some selects, and we try to generate or insert a customer into a database, and we already have this very weird email address, so we throw an error and we do a rollback and we report this error back to the client. And if we have a non-enormous email, then we can just simply submit this order, and now the order taking service actually responds something as a meaningful information, and also it says that the order will have a price of 24 some currency. So this is the service in working, and this is the demo. So you can be sure that I'm presenting you something which actually is done and it's working in Idris. And you can see that this works on top of Node.js. So that's the technical demo, and let's jump to the presentation. And the presentation starts with this high-level overview of my experiences coming from the software industry. And I was a QA test engineer. I was also a C# developer. Nowadays I'm a Haskell developer, and I gathered many different styles of programming. I was working for startups. I worked for outsourcing companies. I worked for different financial industry. So this is everywhere I have seen different styles of developing projects, but there were something kind of common within these projects, and this was kind of described via these diagrams. So when we say that we are implementing a software project, then we have some kind of requirements, and that is from those requirements we have some kind of quality assurance like testing and validation of the software, and we also have an implementation. But as a software engineers, we think about in different semantic layers, and we kind of design our program differently, because we have the requirements, but we still have to do the modeling of the requirements, and we still have to understand those requirements. And this process happens in what I call a semantic tower. First, we draw a very high-level design, then after we go into detailed design, then we realize what is the data and what is the behavior and how that should behave. And after we go for the implementation, which uses some libraries and which uses some technical environment or technology stack. And usually the usually the technology stack is strict. We cannot really decide what we use because it kind of tied to the company. But sometimes we can also check between different technology stacks. But how this thing is realized in a software project which has multiple actors and multiple developers. Basically, the requirements end up in requirement documentation, or over time some Jira items like issues, like change requests, and we still have just one unified implementation, which is the code itself, and usually that's a flat implementation, and the behavior and the data is modeled in a flat way. And after we also have some kind of testing, like we have a QA test automation team, or we have manual testers, software developers write unit tests or end-to-end tests. So this is the real software project. But when we have this semantic tower in our head as a model, so this is how the semantic tower fits. Requirements goes for this design diagrams and so on. But over time, the software will change. And if we have this semantic tower and we have a change in the design diagrams, so in the requirements, so those should change the design diagrams. Or if we have something as an issue which we realize that we didn't implement something well because there were some miscommunication between the teams, we have to change the behavior. And also we have to change sometimes the technology stack, because even OSs can be replaced, and that cost us many things. And here with the real software project, there is a problem that if I have to change the requirement documentation and the high-level design diagram, what is going to force me to actually change the code or change the libraries or change the test? And the only thing that forces me is the dynamics, how we develop software nowadays, that we read the changes and we understand them again, we understand the current implementation, because within this flat implementation, that like what I said, that in this implemented data and behavior, we have to kind of reverse engineer all this knowledge, because at the beginning of the project we squashed everything together, and we squashed everything to documents, which everything to the implementation of the software. So this is the actual status quo that we do, and that's kind of the best practice we can have. And I think Idris can improve this situation a little bit. But before going there and to see how dependency types can improve this situation, I should talk about domain-driven design and about my motivation, why I picked that. So last year I read this very nice book from Scott Walshin, A Domain Modeling Made Functional, and that's an F# book. And at those times I was kind of trying to look into Idris as well, and I decided, when I understand the domain-driven design and when I start to be comfortable in Idris, then I would like to implement the whole book using Idris. But also what I wanted to do as an experiment, if I can create a technology stack which at the end of the story will just implement something as a function from an input to an output, because that's the high level thing, that how we model software, from input via some effectful outputs. And the domain driven design encapsulates the software design into a very nice and unified framework, which says that the software can be implemented in terms of bonded context, and different subsystems can be seen as bonded context, and bonded contexts are kind of the things that usually some service do, or some user story around this bonded context. And all this is very detailed in Scott's book, so I really recommend to read that book. But here the high-level overview is that when we have a bonded context and we talk about different subsystems or different services within this bonded context abstraction, then what we see is that we get an input as a command, and based on that input we select some behavior which is called workflow, and we execute that behavior, and it is going to generate an information about the events which happened within the behavior, and that information is kind of propagated to the subsystem or to the next system, or the next bounded context, and we can build this bounded context kind of horizontally and vertically, because I can build workflows up from even bounded context. So this modeling has this very nice fractal nature where we can actually zoom out and we can still use the same terminology, and that fits really well to the functional programming. And Scott has showed that, but I wanted to be like super type safe about this and model this relation in Idris. And the good news that I was able to do it. And the example here in this order taking repository, and you can also look into the details. And jumping a little bit or zooming into this domain-driven architecture, that the most important thing are the workflows in this bounded context or in this DDD. And this is an example which is around the book. The book is built around this example, and this example is how we place an order in this order-taking system. And what we actually get, that we get an order form, we can validate that order form, and we can decide if the given order is an invalid order or a normal valid order. If we have a valid order, then we can simply price it, and we get the info. We can send the information to the customer that the order was okay. So that's what you have seen. And also we can simply create an invalid order, which we create more information, do more things there, and after we render some information that order was invalid. So that is the information flow, and we still have this input to output pattern, but because that's how software works. But what have you seen already at the demo, that how this microservice works? Than what I implemented, and it basically gets a JSON, gets a request, turn that request into a JSON, parses that JSON into a JSON data, and after we also parse this JSON data to actually a command, which command will select a workflow, and that command also creates the workflow input, and the workflow is executed, which talks to a database, talks to different services, creates some information, and we have the workflow output where we create an event, and from event we can create the event data, and this is kind of important because we are filtering out information that shouldn't be leaked out for the user. So this was also mentioned in Scott's book, and I learned it from that. That's actually a really good idea to separate the event data which goes for the user or for the customer from the event what we created inside. And from the event data we create a JSON and we send the response. So you already seen this working. And I used Idris. But why I used Idris? Because I think within this semantic tower, Idris is a very strong programming language where we can use dependent types, and we can use dependent types to model actually every layer of this semantic tower. And what we can do is to implement something which connects the different layers in this semantic tower as functions. So I can write a design diagram, and I can write a detailed design, and I can write a function which maps the design diagram into my detailed design. And I also can do this with the data implementation, data behavior definition, with the implementation, and so on. So, and why this is useful? Because every change that I do in the software that will actually propagate up to the design diagram and down to the tech environment if the propagation is needed. So I have this very strong explicit link between my different layers of the model, and that gives us a very nice power. So let's jump into the implementation details. So as you remember, we had this workflow which validated an order form and turned that into some order information. And that was the graph which was written which could be written like this. We can create a simple DSL overloading Idris's do notation. And with this DSL represents a state transition system, and this represents the same graph. So we can firstly validate the order. We can check if that's an invalid and do something if it's invalid, and if it's valid, then price and send acknowledgement to the customer. But this is this very high level overview of the workflow, how we can turn that into a function which can be executed. And because of dependent types, then I simply can create a function which turns this workflow into an A to MB, input to monadic output computation. And because I have the power of dependent types, and here the workflow is the indexed data type, and this index data type represents this very simple DSL where I can have state, and the command is a simple state transition, and the check is kind of the branching state transition. So I can create this dependently typed record, which tells me that how to map the actual state of the state transition to a real Idris type, and how to map the step to the functions from A to MB, and how to map the check into another form of A to MB, which is also has the branching information here. So if I don't use dependent types, I still write this model on paper. If I don't use dependent types, I still write these functions on paper and I glue them together, but the connection is lost because this high-level train of thoughts actually are on paper and I'm writing something as a code. And if I come back for like a month later, I have to reverse engineer what was here in this state transition system. And actually, this is not what we write. We usually write the full state transition, not just the step state transition. And that is that is harder to understand because you don't have kind of these reference point. Usually you go for Jira, like git blame, getting out some Jira items, reading some documentation, realizing that idea came from some of these high-level ideas like this place order workflow. So this is already useful because you can join this definition, the definition of the workflow, with the actual implementation of the workflow, and this is done via how you implement steps and how you implement checks. And what is the simplest architecture that can be written via this way? And if you want to use like third-party libraries I used from out of the box, you can simply go for Idris generating a JavaScript which can be executed in NodeJS, but NodeJS have this async architecture, and for this async architecture you have to write a promise monad, and on that promise monad you can write your state transition system, and you can call it place order monad, and you can simply say that yes, this is the place order workflow, and this is the morphism between the place order workflow and my actual implementation. So we can try this kind of extrinsic state transition, extrinsic proof that my implementation has some kind of connection with my original idea. But I went a little bit further because the book only has this example of the place order workflow, but also talks about the bounded context. But the bounded context was not that defined or not that like type safely explained in the book. And what I wanted to do is to actually use Idris's dependent types on formalizing how the bounded context and different workflow can be put into the same into some of the same computational context, but also using separation of concerns, because if you have different workflows, it's not necessary that all the workflow would share the same database, would share the same set of services. So I also did that experiment, and you will see soon how it is done in Idris. So I just really wanted to go for, okay, I'm going to give even for the dependently typed function dependently typed version of the bounded context, which can include the placeholder workflow. And because I didn't want to immediately jump to the implementation of the placeholder workflow, what I did, I introduced the placeholder DSL, which is a free monad, and you will see that soon. And that free monad idea is interesting because Idris is openly a multi-backend compiler, so we can compile the same code for chess scheme, we can compile the same code for NodeJS, and these are like the official backends. But there are unofficial backends, like somebody is writing the JVM backend, somebody is writing the Python backend. So that gives us the ability to even think about the opportunity to write the same software but deploy on different architectures and different technology stacks. So I can, with this free monad approach, what you can do is you can define how this placeholder workflow actually works and what are the steps that, and how this domain is kind of defined and implemented in terms of the primitive operations of this placeholder DSL. But you don't tie yourself just only one implementation, because you can give different implementation. If you want to replace the technology stack with this, we can easily do that, because Idris allows us to generate code for different backends. And in my very example, I use this DSL, and I have an interpretation of that DSL, what I call placeholder backend monad, which is a simple monad transformer of an accept T and reader T over this Node.js promise. I also have some database monads, which also sits on top of this promise monad, and the rest of the technology stack is the Node.js. And I also use Node.js to experiment with FFI, how hard is to FFI with random JavaScript libraries, and the answer is not that hard, and you have to just write simple wrappers as these FFI calls, and Idris FFI here it also shines. So I was really satisfied that I didn't have to do too much head scratching there. Okay, another implementation detail finally. So we have this very high level description of the bounded context, where we can say we have a type which describes a command, we have a type which describes workflow. Within this bounded context, we another type which describes an event. But we can also have, because this is a dependently typed record, what I can simply say that I have a function which associates the workflow with commands with workflows and commands with events, and this is going to be used in the bounded context implementation, which is a collection of the type safety parts of this very simple algorithm. And this very simple algorithm, basically the same chain that you have seen previously when we get a request and we turn that request into command data. And this is just the steps. From that command data we create a command, from that command we create a workflow via some steps. From the command and command data we also create the input for the workflow, we run the workflow, and if we get the result, then we turn that result from the workflow, if that was an error, to a bounded context error, and if it was something as a normal value coming out from the workflow, then we turn that into a context event. So here, what I said that what I wanted to do is to simply say that if I have this bounded context implementation, which all the collections, which is actually the real implementation of the workflow and the real implementation and the kind of the boilerplate things, or like the scaffolding things around the data processing, then I can simply turn that into an input to computational output, and this is very, very strong, because whenever I change something, Idris will tell me that, okay, you have to change those modules because I'm not going to compile that anymore because you changed the underlying type, so you have to adopt these things. And I collected here the full architecture explained, and I'm going to add more and more documentation over the time. So that's my next step with this project. But I really wanted to present this for you regarding not having the documentation yet, because you can read Idris, you can learn Idris, and the next in the next session we are going to talk about like the dependent types in action, that actually how I use dependent types implementing this microservice. So you already have seen this workflow, which is the already boring workflow for you, because we have this morphism, and we use this morphism to turn any workflow into this monadic state transition. But the workflow, I wanted to describe this or show this, the actual definition of this monadic workflow, or the high-level workflow definition, that yeah, this is a simple index data type. I just do this. This is my step, this is my branching, and one step after another, and this is the way, because we overloaded this operator. Simply a do notation will work for us. And the next thing here is the actual example for this workflow morphism. So the workflow morphism for this workflow, which was there for these steps, then a morphism which is going to work on inside the placeholder DSL, and which DSL is the monadic, is the free monad like DSL, and it will operate on this state, the overview, the high-level overview state, and well, I didn't have too much imagination, so I just called the command as step and the check as check. And what we can do, it's not surprising for an Idris developer, that we can turn this data type definition into actually a function which computes a type from these constructors, and that's the way how we associate these. So if you remember with the validate order, what we know, that we got an order which was either an invalid order or either a normal order, and from this, for the valid order meant to be a domain order, and an invalid order meant to be a domain invalid order, and the branching was happening on this order. And you can see the order info is the same as the list of placeholder events. So here I can easily mix and match between the actual simple monadic implementation and the very high level overview of the actual workflow. And of course, I can write this function, which the input type for this will be computed by the state type computation, and the output type will compute at the same state type computation. And I can simply call functions, but because I'm in the monadic part of this placeholder DSL, then I can simply use the do notation as well. And this is very straightforward. Of course, you still have to implement the validate order, you still have to implement the price order, but again, here we have another explicit link between the workflow and the detailed definition of the workflow and the data and the behavior, because here I use the free monad to detail the behavior without giving any implementation of that place order yet. So let's see the most complex part of the repository is the bounded context implementation. So if you remember, I said that for the bounded context, we can create a simple record which says what is the command, what is the workflow, what is the event, and how these are kind of connected to each other. And in the Scott's book, this is trivial because we just have one bounded context and we have just one workflow. So the mapping and the types here will be trivial, and one would say that it's not necessary, but here it's more like, this project is more like a blueprint for a much complex project, and you can steal ideas and you can kind of scale down or scale up all the abstractions that I introduced here. But again, let's jump into the bounded context implementation. So the bounded context implementation must consist some information about the bounded context which implements, but using these types here, or using this information, we can simply say what is the workflow environment for the workflow within this bounded context, or what we named here in this bounded context, and what is the type for the command, what is the type for the event, and so on and so on. And I still had to do the little technicalities from the execute command, and that was more like for every workflow could have its own monad type, because as a reminder, my goal here was to do as much as the separation of concepts then as possible, and that means that every workflow can have its own monad. And surprisingly, what I was able to do is to say for this workflow monad, I actually captured the monad instance within this dependently typed record, and I was like, wow, that's really nice. Another wow moment for me when I started to use simple expression to define data types and define types. So coming from different historical programming languages, like historical in the sense that I used them previously, then this was something as really nice, saying that I can use the same language at type level, then I can use the same language at value level, and there isn't too much of a difference there. And I had to and because I have these different monads for different workflows, and I had to talk about how to embed a workflow monad into my monad, which implements this bounded context implementation. But that also can be done via some embedding, and I'm going to show that part soon. And it's a very simple thing. So these are the bits and pieces which made the execute function type safe. So I already said about this, my wow moment. And this is linked again because I really want to stress that this is a free monadic representation or definition of the placeholder problem, and I solved that extracting what are the primitive operations in this domain, and that's only what we have to implement. And the primitive operations in the placeholder domain turned out to be, yes, we have to be a monad, or we can throw and catch some errors in some cases. For example, when the product has more than one line, and when one of the lines errors out, then we don't want to process just stop the processing, but because we need some more extra steps, so we need to catch the error and act on that error. Somehow we have to create new IDs, and somehow we have to decide if a product code exists, an address exists, we have to get a price for the product, we have to place a priced order, and acknowledgement letters. So this is the thing that we need, and from these little building blocks, these primitives, we build up the whole place order abstraction. And that model is very large, and that is in the focus of the book itself. But in my implementation, it was like, okay, I don't want to give in immediate how I'm going to connect to the database, but I'm actually talking about the problem itself, the problem domain itself. So this was another separation of concerns, because I didn't want to stuck to one database implementation, one address service implementation. I just wanted to say that, okay, this is what I need to actually go and implement something. And because of this is a simple free monad DSL, then there is no need to talk about effect systems here, because here we are just talking about the domain itself and not the realization of the domain. And for me, it's kind of appealing to use these abstractions, because what we can do here, we can easily adapt and experiment the implementation later on, and hope to connect this with some actual real computation, is that we can simply say that if we have this very high level DSL with these primitive operations, then what we can do, that we can give a model and we can just use the same types and the same constructors from the DSL, but instead of adding a DSL type here, we can simply say, okay, that's the monad. That's a monad here, and that's how I'm going to interpret my DSL using this model. So you give a model which will implement your DSL, and that model is able to talk to a real database. And that's not rocket science either. And we didn't really use too much of the dependently typed features of Idris here. So we can zoom a little bit down, and we can go a little bit down, and we can talk about the actual implementation of the model for this DSL, which I call the backend. It's not really imaginative, but yeah, that's a backend implementation. Maybe I'm going to rename it soon, but the structure will stay. But that implementation is basically a reader T and an accept T because I had to handle some exceptions, but the reader T is the actual dependencies that I have to handle, and that dependencies are kind of organized within components. And this is another nice way of using dependent types, because we can simply group together functions and the types that those functions actually handle, and with this approach, we are not leaking abstraction out from the component. So we are not we don't have to parameterize that the type with this email error. We don't have to parameterize the type of the DB connection, because we can simply hide these away. And when I have this monad transformer stack, where my components are actually dependencies in this sense, then I can simply say that this is how I'm going to use these little components. But when I instantiate these dependencies, if you check here, then what I can do, that I can have an order component, but my dependencies also immediately has an order DB connection, and the type of the order DB connection comes from here within this type. And I close this abstraction of the dependencies, so I'm not leaking anything out, but actually I can reuse this type here. And because I have a way to create a DB connection via this init connection, my run backend function is able to create the connection when it gets evaluated, or when it gets kind of instantiated via the workflow selection in the bounded context implementation. So this was a very nice way of actually closing out another separation of concerns, closing out those details and boxing them into this very nice component pattern. And this was also in Scott Warshin's book, and I don't know how, and I don't remember how hard was to implement that in F#, but it was super easy to implement in Idris. So another really great example of dependently typed, like dependently typed programming, actually making something which is understandable and easily usable. And the next thing, that another reason why I use this component abstraction, because I learned from my experiences that testing is hard, and in many cases you have to do dependency injection for when you do unit testing, end-to-end testing, because in the test environment you are not always have all the services available, and in your test script sometimes you have to script these components, actually how those components works and how they react. And some of these things that what can be done here is like you can even write a component which replaces a real workflow or a real information flow from a real service. And this is easily done in object-oriented languages, because in object-oriented languages you can enclose these abstractions and you can hide those types away. But it's hard in other statically typed functional programming languages. But here in Idris, I realized that, oh, I can do the same thing, like what I did in C#. So why not to do that? But even with C# and with Java, when you have these dependencies, like usually those are hidden via interfaces, those dependencies needs to be injected via the constructor or via some kind of dependency injection framework. And here I realized that, oh, but I have simple implicit parameters, and that means that I can inject these components as part of like normal implicit argument. And what I have to do, I don't have to write these components as part of my mkrun backend as normal parameters, but with implicit parameters, Idris will know if it sees something in the context, and if it's unique, then it will just wire these components in, like it wires via this embedding, within this embedding. And this is really good, because this helps us to create the test suite which would test my backend abstraction. Simply say that I'm injecting these components, and this is the email test component. So actually I validate that I got an email and so on. And this is very powerful, and we shouldn't forget about this very pearl of the implicit parameters. And another of my learning is the embedding of normal types, or like embedding of computations, not normal types, but normal like monadic computations, where I wanted to say that, okay, this is something as like a natural transformation niche part, where I have one monad and I embed that to another monad. But because Idris is dependently typed, in a sense that these type parameters are better if they are present there, rather than learned from the context. And it was hard to write this abstraction without this type here. So and after a little bit, with many helps from the community, then I learned that, oh, what can I do is actually I can create this run embedding function which unwraps this internal and applies the type A, and this type A is actually learned from the expected type of my client code. And this was a really nice trick, and I really wanted to talk about that. And the next step, even we can go further, and we can say we have a type safe. We can represent SQL commands in a type safe way. And first I didn't do this, but after, when I finished the first version and it was working nice and sent data to the database, then after that I was like, maybe I can improve the SQL commands as well. So I can improve the abstraction around SQL. And this SQL abstraction is very simple. You can see that we have a table which has a name, which has fields, and has some constraints. And I'm going to improve the valid table property, but that's something for the future. I know it's straightforward because I have done something similar with the select, but That's also not detailed here, but it's there on the code. So if we have a table, we can simply create an SQL command, which is a create table, or we can create an SQL command, which is we get a table and we get the values of actual type which computed from the fields. And why this is important? Because if I have this table definition here, and if I have this insert command here, whenever I have to change the table for some reason, that the insert, the original insert code is not going to compile anymore, because this the type of the field list that I'm going to insert into this product table is going to change with the product, and Idris tells me that, oh, you changed the fields, so you also have to change this insert as well. And if you see that here we have four arguments, but here we actually have 3 values to insert. And this is because this is an auto increment, and even you can simply say that the insert values, which computes the list of types within this expected age list, heterogeneous list, then also can skip values, and it skips the auto increment. So this is very nice. And the next step, of course, to turn that type safety into the select SQL command, select SQL query, where you can write something like this. So select these fields from the product table where you have these constraints. Of course, I still have to improve the constraints, like the operations, and I can still introduce type safety. I didn't do that, but it's on my to-do list. But what I already introduced is that I can create a well-formed select in a form that if I know that this table here, I have this table here, and I'm looking for these fields from this table, I also have to create kind of the implicit proof that these fields are in the table. And writing this proof can be done in using index data types, and it was something easy, like a few liners. So that's why I didn't include here in this presentation. But the nice thing here, that if we are using simple constant like data, then Idris is able to get this kind of proof for us. And the another one is that the OK filter, which says I'm filtering for the fields which are in the table. And the NodeJS SQLite API, when it runs a select, it returns a JSON for me. And the next step for me, it was like, okay, if we have this JSON, I want to be sure that JSON is actually well represented on my client code. So every client code which depends on the return JSON, then I should act on the structure that I get, and I should do the validation step if I'm working with the right JSON schema. So I fired up again the index data types, and I created this in JSON index JSON, which helped me to write a client code on select. If I change the table, I have to change the client code as well, because the compiler will tell me, okay, something went wrong here because this field is not existing anymore. So you have to think a little bit harder. So with these dependent types, you can see that we have this very high level description, and because of every layer, even though we are talking about functions which even for client codes, for SQL queries, can be connected to each other if the developer wants to connect it. And that's very strong and very powerful, and because of this explicit connection, we have a very nice maintainable architecture. Another surprise for me was the postfix notation, which kind of guarantees the O feeling. And I just only use this postfix notation of functions when I have an API via FFI, and that API is object-oriented, like many JavaScript libraries have this API, and you can simply kind of mirror that API using this postfix notation, and it gives you this very nice object-oriented readable code in a sense that this is more recognizable if you look into the documentation of the original library, and it can be replicated the same look and feel in Idris. So that was really nice. But I left the most surprising part and the most surprising experience that I had with Idris, and this is kind of, it was good and bad at the same time, because many statically typed programming language gets criticized, but because it's not as dynamic as JavaScript. It cannot do things like you would do in JavaScript. But because Idris has this first level citizens as types, then we can do pattern match on those types, and we can do this kind of crazy dynamic type programming if you want. And in what cases that you really want to go down that path? For example, if you have a strict deadline, and in my case this strict deadline was, yeah, it's already 10 p.m. I really want to go to sleep, and I don't want to prove that all the fields in this values will actually have, all the fields in this insert values will have actually the right type. Because the problem here was the the optionality of SQL types, and I didn't have mental energy there to actually express that at that moment. So what I did, I just simply wrote this very recursive function which recursive on types, and I have this very few types, and I was like, yeah, I'm going to, I know that this is going to be the only thing here, and because I have this obligation, because I'm pattern matching on types, then if something goes wrong, then I just render a stupid string. And because this was an SQL, that was the most appropriate string that I could find. Yeah, flipping tables. If you are working with wrong SQLs, then you should flip tables. And I ran the test suite, and I got like insert into flipping tables, insert into values, flipping tables, and you're like, what? Because I forgot this line, and that meant this was not met, the insert here, the fields from here was not matching any of these, so it was like these flipping tables. And at that point I was like realizing, oh, I forgot this. So I did the same mistake that I usually do if I'm tired, and if I'm using a dynamically typed programming language, then I forget some kind of instance of case or these kind of things, and I get a very nasty runtime error. And Idris, and this concluded me that Idris is strong as JavaScript, and this is the argument that you can use if somebody wants to use that argument against statically typed functional programming, that it's not as strong as JavaScript. I proved that it's as strong as JavaScript because you can make the same errors, and that's a very strong statement. But this is not lessens the shine of Idris. It was just more like me as a very tired developer doing something stupid. But why this is nice? Because you don't have the proof obligation when you talk about types. So that means if you have a tight deadline, you can do these kind of things, and after you can come back and fix these proofs later, or these kind of constructions later, and you can introduce the actual nice type safety or the nice proofs that actually is needed to close out this shouldn't happen case. And that's the end of my talk, but I also want to say some words, because what I learned during this process, if I have to summarize it in one sentence, that sentence would be dependency type programming is not proof engineering. Because I implemented a very complex dependently typed abstraction around the bounded context, which now it's kind of the bounded context turned into this mathematical object where we actually have a function implemented around them. But I didn't have to do any proof engineering or any proofs related to using Idris libraries, and Idris really shines here. So Idris gives you the opportunity to do proof engineering if your domain needs, but Idris is a programming language and the technology which can be used even now to implement microservices if you decide to use the Node.js backend, because you will have these many libraries, JavaScript libraries at your hand, and it's very easy to write the glue code for the FFI. So that's my conclusion. Idris is a really good programming language. It feels really natural. It feels really easy to work with. Functions which actually associate types. It's very easy to work with index data types, and you can write complex software with it. So that concludes my talk. Thank you very much for your attention. And let's go to another room for the questions.
Thanks.